Welcome back today. Today we're going to be doing LeetCode number 875, Koko Eating Bananas. And this is like a very common LeetCode question that's asked in a lot of companies. And basically what the question is asking is that there's an animal, Koko, who likes to eat bananas. And you're basically given this array here where each indice basically denotes how many bananas are in that specific location or in a specific pile. And basically you're given this H, which is basically the amount of time that it takes for the guards to come back to the piles to check if any bananas have been eaten and such. So you want to basically find the answer is basically going to be the amount that Koko eats per hour. So this is basically that's K. So K is the bananas eaten per hour, and you want to find a minimum integer K such that she can eat all of the bananas in each of these piles in the given 8 hours or the H time before these guards come back. So to learn more about this, let's go to the iPad and figure this out. All right, so let's get into the iPad explanation here. So again, we're given this piles array or vector, and then we're given this H. And we want to essentially find how many bananas per hour can Koko eat so they can eat all the bananas in these 4 piles in this example in the given time, which is 8 hours, right? And so that's why our answer is the K value, which is 4. And so I'm going to write this example down here for 3, 6, 7, and then 11. And let's talk about how we do this. So first things first, we need to know how we're going to actually calculate how many hours it takes Koko to eat all these bananas. Well, let's just say we have an arbitrary rate, which is K is equal to 5, right? How do we calculate this? Well, it's just simple division here. So what we're going to follow is this formula. Ceiling of piles at I divided by this K value. And I'll explain why this works. Well, one thing the question tells us is if Koko were to come to the first index, or the 0th index here, well, there's 3 bananas. Koko eats at 5 bananas per rate, so they could eat this in 1 hour, but they cannot skip to another pile. So Koko might eat this in less than an hour, right? But they cannot just go to the next pile, right? That's not going to work. So the thing is, every pile, every time they eat bananas, they have to stay there for the hour. So in this case, Koko can eat this in 1 hour, right? Same thing here. 6 in 1 hour, he'll eat 5. He or she'll eat 5. And then they have to wait another hour because they have to eat that 1 more remaining. So it's 2 hours here. 7 again is 2 hours because there'll be 2 remaining after eating 5. And then 11, they'll eat 2 hours, so they've eaten 10 and there's 1 more left. So it'll be 3 hours, right? And this is considering K is 5. And that works out because you see it's basically what the math that we're doing is 3 divided by 5 and the ceiling of that. And that ends up to be 1. And then you can check it for the other ones as well and it works out. And you can see that this actually adds up to being 8, right? If you add all the hours up, which is exactly what the H is, right? The H is 8. So it adds up properly. So we can see K is equal to 5 would work. This is an answer. However, the question wants us to give the minimum K value. So we can try this again. Let's say we have K is 4 and then K is 3. We'll do that for all of them, right? And so now if we do that, so 0th index, K is 4, still will take 1 hour, right? 6 will also still take 2 hours. 7 also takes 2 hours still, and then 11 takes 3 hours as well, which is 8. So as you see, this also works, and this K is smaller. So this is actually our answer so far, right? Then again, we'll try for K is equal to 3. So K is equal to 3. This takes 1 hour. 6 takes 2 hours. However, this time 7 will take 3 hours because they'll eat 6 in 2 hours, and there'll be 1 left over. So this will actually take 3 hours. 11, they'll eat 9 in 3 hours, but there'll be 2 left over. So it'll take 4 hours. So we add this up, and this is 10. And this is the point where you see, hey, anything smaller than this K value is not going to get us to our answer. It's not going to get us to H is 8, right? So we see at this point, it's kind of like a splitting point. So K is equal to 4 must be the smallest possible answer. And you see that that's the answer that's given. Now, what did I really do here? I kind of just did a linear search, right? If you think about it, I did a linear search from 1 to, essentially, I would have gone till 11, right? I know I went backwards for 5, 4, 3, but I would have gone from 1 all the way to 11. And this linear search, right? And at every point, I'm assuming that this linear search, the value of this, the numbers that I'm going through, are actually my K values, which is essentially my answers, right? So I'm assuming that this is actually, if K was my answer, what would be the hours that it would take? That's essentially what I'm doing. So if you actually find the time complexity for this, it would be n squared because it takes you, or not n squared, essentially it would be n times m, basically where n is the size of, the piles, the number of piles, and then m is the range, right? And this makes sense because essentially you're going through every single element, the range basically from 1 to 11. And the reason I said 1 to 11 is because that's the max in this piles. If it was like 25, that would be the max. But yeah, that range times the number of piles that you have, which in this case is 4, right? So that would be the time complexity. And this is honestly roughly like n squared if you want to think about it that way. Like it's a quadratic time complexity, and this wouldn't really be accepted by most companies, right? So here we see a linear search and we want to make it better. Well, what if we do a binary search, right? That's what I'm thinking, right? Because that makes my time complexity better. Same, right? The ranges don't change. But this can make it actually that essentially we're going to do a binary search on the range, right? So I still have my n piles times my log of n, which is the range, right? And this is better. But let's think about how we actually do this. And what is this actually? So this actually is a concept called binary search on answers. And usually binary search comes in a couple ways in question types. One is like straight up binary search, where you search for a specific element in a vector or array, or something like this, where you have basically you can do a binary search on the possible answers and figure out which answer fits your criteria. And it usually has to do with like when you're trying to find a minimum of something, maximums, that kind of stuff. So in this case, how would we do a binary search? Well, we would start at the minimum, which is always 1. And if you want, I'll write this out for all the way till 11. And essentially, we'd go to the middle, which is here 6, and we'd say, hey, is this k value going to work? Let's say it does work, and we know it will because we know the answer is 4. So this k value will work. That means our left and right, which is here, let me write that a little better. Our left and right, which is here, if it works, well, we know this is a possible answer, but maybe this is not the minimum answer. So what if we move the right to mid -1, right? So essentially, we move right here, right? And the mid is gone, this right is gone. And again, we go to 3. We're like, hey, does this work? Well, we know 3 doesn't work. So, hey, we're going to do left is equal to mid plus 1. So now our left pointer is here, right? And we check, hey, middle, which is again 4. And we're like, yeah, this does work. So then right again goes back. And as you see that the right and left have overlapped, which is usually like our binary search condition, right? Left must be less than or equal to right. You see it overlaps, and guess where our answer is at? Our answer is at left. And this will always be the case, because what happens with these answers is like the pattern here is like, you know, after a certain point, all these answers work, and before the certain point, none of these answers will work. So where that overlapping or that change in polarity or parity, whatever you want to think of it like that, that change, that's why I drew this line here. That change is what signifies that this could be a binary search question. And this overlap is where we can see that, hey, our left is going to be at the answer. So let's get into the code and let's code this up. And one more thing before we go there, actually, the time complexity, as I said, would be n times log m, which is essentially the best time complexity. And there's no space complexity here, essentially, because we're not using any external space. But yeah, let's get into the code. All right, so let's get into the code here. So reminder, I'm doing this in C++, but you can do this in any language. The concepts will transfer over. One more thing to keep in mind is that in the constraints, they tell us that the piles at I and also the length of the amount of piles can go up till 10 to the 9. So maybe we want to use long here. And that's actually like one of the reasons that there are a lot of bugs on this question for a lot of people, is because you need to actually use long on this question. But yeah, anyways, let's get into it. So first things first, I'm just gonna write another function to find the max in my piles. It's just cleaner code that way. You don't actually have to do it. You could also put all that code here, but it just makes it a little bit more cleaner, I think, to separate it out, because like what I'm going to do is like the middle of this is just going to be all the binary search. So it makes it more clear. But yeah, all you need is the piles vector, and I'm going to have initialize a long, call it max value. Oops. And then just say it's like the minimum, it's the minimum value. And essentially we're going to go through the entire piles vector and compare it. Like we're going to check, hey, is my piles at I, is that greater than my max value currently? And if it is, we just set our max value to that piles at I, right? That value at piles. And then return the max value, right? That's just giving us the max number in the piles vector. So now we need to set up this binary search, right? Which our left pointer will be pointing to 1, right? And our right pointer will be pointing to the max of the piles. So essentially we call our function, and then that gives us the max, right? And now we're going to set up the binary search, right? So left is less than or equal to right, just like how we normally do it. And then we also want to calculate the mid. And in this case, I'm going to use I've talked about this in other videos for like binary search, but another way to find the middle point is to do this instead of doing left plus right divided by 2, because when you're dealing with adding larger numbers, sometimes you can overflow. And if you overflow, this mid value is going to be wrong, right? So subtracting them ensures that you're not going to overflow here. But yeah, you could also do the, I think you might be able to get away with this one as well, like left plus right divided by 2. But yeah, I'm going with this here. And then remember that this is actually our answer, right? So the mid value in our case is not actually a index position or anything like that. This is actually our answer. Like this is a possible answer. So essentially we're going to simulate, hey, if this was my k value, right? If this was my k value, what would the hours be? And and then accordingly we move our left and right. So in order to find the hours, we're actually going to have a function. So we're going to call find hours. Again, this is to make it more clean. Remember that your interviews are not just about writing the right code, it's also about writing clean code, right? That also matters a lot to the interviewer. But yeah, what I'm going to do is I'm going to pass this vector, right? We need the vector in order to calculate that hours, and then we're going to give the k value, right? So let's write this function here. So find hours, right? And we pass in this vector, right, piles, and then we pass in the k value. And this should be a long here, long k value. And then we're essentially simulating, right? It's that formula thing that I talked about in the iPad explanation. So essentially we go through all the piles, right? All the numbers in the piles. And essentially we're basically going to add up the hours, right? So hours plus equals, and we talked about this, is the ceiling of piles at I divided by k. However, remember one more thing. When you do this division, it's integer division. So we want to still have it be a decimal value because, like for example, 3 divided by 5, it would actually give us 0. Finding the ceiling of 0 is just 0. But if it's a decimal, which is 0.6, it'll do the proper ceiling. So exactly, that's why we just need to typecast one of them to a double, and it'll do it for you. And then at the end, we just want to return the hours, right? So we have the hours here. We have the k value. Now we want to check, hey, after we simulated, is this hours less than or equal to h? What does that mean? Well, that means we took less hours than we had, or we're exactly equal to h. That means that we have a number k, which is either it is a valid answer, but it might not be the smallest answer. So in that case, we want to move right to mid minus 1. Else, that means hours was greater than h, which means that this cannot, we can't have this. So left must be mid plus 1. And we saw in the iPad explanation, this left right will keep moving until they overlap, and left will be at the right answer, right? So left, whatever left values, that is the answer. And this works because that is actually what we're doing, right? We're doing a binary search on answers, right? That's the whole point. So these are actually the answer values itself. So let's run this, make sure we don't have any compilation errors, any syntax problems here and there. As you see, it runs these 3 test cases. Let's go ahead and submit it. Make sure we pass all the LeetCode test cases. And as you see, yeah, we do. And yeah, so this is going to be basically like an n log n solution, or to be more precise, n log m. But yeah, let me know in the comment section down below if you had any questions about the explanation or anything like that. Let me know if you want to see any other LeetCode questions that you're struggling with, anything like that. And I'm also going to be making a lot more like tutorial videos on like different tech stacks and stuff. So stay tuned for that. But make sure to like this video, subscribe to the channel, and I hope to see you on the next one.